Okay, so far we've been talking in this course about two kinds of homology. The first we introduced is simplicial homology. Where X is some simplex, or more generally a delta complex, right? And we have this notion of simplicial homology. And then we introduced this notion of singular homology. Here, your chain complex are just each like delta. Your chain complex here, your delta n is just all words. X has some skeleton, an n skeleton, which is made up of simplices, and delta n is just all of your n-dimensional guys in your n skeleton, right? So, for example, with a sphere, lots of ways to think about a sphere. One way you could think about it would be up top and bottom, you have two copies of two simplices that are glued along the equator, right? So on the top, you have this two simplex. On the bottom, you have this two simplex, and they've been glued together. So there your delta n, for like delta 2 would be z squared with these two as your generators, right? And your delta 1 would be z cubed, because there's three 1 simplices. And your delta 0 would be z cubed because there's there's three zero-dimensional simplices. We got through that? Okay, good. Whereas over here, with singular homology, we instead think of a sphere as a space, and then you look at all of the maps, sigma, from delta n into that space. So you maybe would be thinking like sigma for delta, for C2, it's generated by all of these maps of a two simplex into the sphere. All continuous maps. And like, there's a ton of those. So C2 is pretty unruly, right? Okay. So that's a story of simplicial and singular homology. What we saw was in the case of spheres, these actually come out to be the same. We calculated out the homology of spheres using singular homology. This was maybe, 2 or 3 lectures ago. And we saw it's exactly like what it is for simplicial homology. I think there was one other case where we could calculate singular homology, and that's like H0 of things, right? And we saw that H0 is just counting the number of path-connected components. So, we understand H0. We understand in general they're the same for spheres. But what if you have some other space? A torus, whatever you want. Is your singular homology going to come out to be the same as your simplicial homology? We've been kind of suggesting that it is, hinting that it is. Well, today I want to give you an outline for the proof that these really are the same. Okay, and it won't be bad because we've already built up a lot of the machinery for it. So here's the proof. What we're going to do is we're going to look. Okay, so the basic format of the proof is we're going to do induction on K, where K is the K skeleton xk. So here, to even talk about simplicial homology, I'm assuming here that X is a CW complex. So X has some nice X, say, is a delta complex. So you can represent X with some K skeleton. Now there's ambiguity. I gave you one way of representing the sphere with as a delta complex. There are other ways you could represent the sphere as a delta complex as well. Well, what this is telling us is it doesn't matter which structure you pick, they're all equal to the same, right? So you can think another way of what this theorem is proving is just showing the homology is independent of your choice of delta complex, because they're all going to be the same as your singular homology. Okay, but if X is a delta complex, which you need it to be to talk about your simplicial homology, then it has some K skeleton. And we're going to do induction on that K skeleton. In the case the K equals 0, what is x0? x0 is just points, right? And we already know that hn of delta of x0 will just be 0 if n is anything that's not equal to 0, if n is something greater than 0. And if n equals 0, what does this give me? Well, it gives me one copy of z for each point that I have. So let's say like z to the m, where you think about this as being m points. So you get a copy of z for every point that you have. Okay. You could also think about the infinite case, then just an infinite direct sum. But I'll just think here in a finite case where you have m points, or z to the number of points. But we've already saw that that's exactly the same thing for singular homology. So a couple classes ago, we talked about singular homology, and we said that singular homology behaves the same way, that hn for a point will, if it's h0 of a point, it's just counting the number of path-connected spaces, so each point is its own path-connected space. And if it's anything bigger, well, then it's trivial. So you should think about this definition of singular homology, convince yourself this is true in this case. Or go back and review the lecture, I believe we discussed this. So this case, no problem, easy. So now we want to induct. So what we're going to do is we're going to assume that this is true for k, and we want to show that it's true for k plus 1. Maybe I'll assume it's true for k minus 1, just because I like how it looks better. And then we want to, so we're going to assume that hn of x to the k minus 1 in simplicial homology is the same as it is in singular homology. And then we want to show that this still holds for the K skeleton. And this is a statement that's true. Is that good? Oh, my bad. Simplicial and singular. And we're assuming this is true for all n. For all n. And we're trying to show this is true for all n. For all n. So, this is also true for n minus 1, or for, n equals 2, or whatever. So this is true for all n. And now it's going to show that this is true. And so how are we going to do that? Well, I'm going to use these long exact sequences I've introduced before. So we have a good pair, xk minus 1, xk. Where recall by good pair, I just mean xk minus 1 is a nice subspace of x to the k, right? So the k minus 1 skeleton just sits inside of your k skeleton. The k skeleton is everything up through k, so this is everything up to k minus 1, so yes, this sits inside of here. And so this gives rise to a long exact sequence. And we can write the long exact sequence in homology, so in simplicial homology. So we could also do this in relative homology if you like, but this just comes out to be okay, I'm going to write it like this. hn plus 1 of the pair xk, xk minus 1. And then this maps with this kind of mysterious boundary map into down to hn of x to the k minus 1. And then the inclusion map induces a map here to hn of xk. And then you can think this is like the quotient map inducing this, although this is relative homology, Hn of x to the k minus 1, and then this like mysterious boundary map that we defined in the previous class again maps this to 1, 2, 3, 4 to Hn minus 1 of x to the k minus 1, and it keeps going, blah 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 blah, keeps going. But we have this long exact sequence, right? Okay. By the exact same construction that gives us this long exact sequence, we can play the exact same game with simplicial homology. And so we have the exact same exact sequence up here. And for all of these, this is now in simplicial homology. So we also have this nice n minus 1 simplicial homology of xk minus 1. So we also have this long exact sequence. Then we can create maps from the top to the bottom where you can think an element of something up here, Hn, is just like some delta n. Well, it's represented by some delta n because this is defined to be, you have to like go back and it's the image divided, kernel mod out by image. But something in the kernel can correspond to some boundary, some delta n, or some cycle, delta n, so you have some representative up here. But that delta n you can naturally map to just the map that sends that delta n into your space as specified by the delta n up here, right? So like this sphere has a delta 2 on top, and then there's a natural map from here, from delta 2 into this map that just puts him on the top, right? So you can think there's kind of a natural mapping from the top to the bottom. Okay, so we get these long exact, this good pair gives these long exact sequences. And with a bit of diagram chasing, you should convince yourself that this is a commutative diagram. So I'm not going to go through it. Although it just follows from naturality. I mean, it's like such a natural inclusion from up here to down here that it's actually, I think, quite clear that this commutes. Like when you map him over, where you just have to remember what each one of these do, this is just the inclusion map in this case. You're just including him here and then mapping it down. But either way, you can see this diagram commutes. What I want to do is I want to show that we have an isomorphism between these guys. Because we're doing induction. So our goal is to show there's this isomorphism. What do we have? I have that there's an isomorphism for k minus 1, or the k minus 1 skeleton. So I have there's an isomorphism here, and I have that there's an isomorphism here. Right? So I have two isomorphisms. Two of them I know are isomorphisms, and I want to get this middle one to be an isomorphism. Well, before we do that, let's step and think about this guy a little bit, and this other guy. So the first and the fourth, let's think about them a little bit. What is this? Well, let's think about a simpler case. So I'm going to think about a slightly simpler case. Lemma. What if your k skeleton was just a single copy of a delta complex? It's just a single copy of a k-dimensional delta complex. A single copy of a k-simplex. So this is just a k-simplex. And then here I'm modding out by a k minus 1 simplex. So you might think it's like a 2 simplex modded out by, the boundary. This would be the boundary of that simplex. This is one dimension lower. So, like, what does that give you? This is secretly just Hn of a sphere. And we know how the homology of the sphere works. That's just the same thing. That's just going to come out to be a copy of Z when n equals k and 0 otherwise. But that's not just true in simplicial homology. We showed that this is the same thing in singular homology. So if you are convinced that taking a k-simplex and modding out by its boundary is giving you a sphere, and we know how the homology of those work, then since these HNs agree for those spheres, we have this statement is true in this case. And so then what you should try to think about, so this is maybe the trickier part, is what this relative homology becomes is it's just a bunch of these guys glued together, right? Something like a wedge product or whatever of these guys. Is it a wedge product? I don't know. It may depend on what this structure looks like. And so I'm going to gloss over this detail, but hopefully like this is enough for you to at least believe that these are isomorphic as well. So you could trace through all these details in Hatcher. But I hope this is like, I'm just trying to wave my hands enough to convince you that it's believable that these are isomorphic as well. Because what I want to spend today showing is, in general, how do you move from these 4 isomorphisms to this isomorphism? So this is really the heart of the proof. There's some nice little arguments. We're assuming these are isomorphic by induction. These are isomorphic because, well, it's an extension of the fact that for spheres, single and simplicial homology agree. But what we really want to show is that this isomorphism follows from the other 4. And it turns out this is a much more general fact in homological algebra. So this is called the Five Lemma. So I'm going to prove this in general. So I really want to spend today proving the Five Lemma, which tells you that given exact sequences in a commutative diagram, so let's go ahead and draw this. In general, I'm just going to call this A, B, C, D, E, and on bottom, we'll call it A prime, B prime, C prime, D prime, E prime. So I'm assuming the top and bottom are exact. Do you remember what it means for the top and bottom to be exact? For the top and bottom to be exact, it just means that the image of this map is exactly equal to the kernel of this map, right? So I should probably give some names to these maps on top and bottom. So let's just call this like I, J, K, L, and I prime, J prime, K prime, L prime. Okay, that's going to get obnoxious having to do those primes every time, but that's okay. And then we have some maps coming down. And we want it to be commutative. So let's give these maps some names. So let's call these alpha, beta, gamma, delta, epsilon. So exact sequence, this is saying things like the image of I is the kernel of J, and so forth, etc. And commutative diagram, This is saying that things like I beta, so first doing I and then composing it with beta, is the same thing as first doing alpha and then composing it with I prime, and etc. That's what those words mean. Then the claim of the Five Lemma is if alpha, beta, delta, epsilon are isomorphisms, gamma is an isomorphism. Good. Which is exactly what we need here. I have exact sequences on the top and the bottom. Commutative diagram. I have that these two and these two isomorphisms. It follows the middle is an isomorphism. Okay. But the Five Lemma isn't just used in this proof. It's used all over the place when you're doing homological algebra. So it's a really nice fact. You can think whenever you have two long exact sequences, you can do tricks like this, where you can see the two of the things isomorphic and convince yourself the other two isomorphic, and then you can use that to deduce what this middle guy is. So it's a really powerful lemma. And what's nice about it is it's just a long exercise in diagram chasing. And so I'm gonna do this with you, and I want us to kind of think through this together, because I think if we can do this, you really will get the hang of how to do this diagram chasing. So I need to prove two things. I need to prove that gamma is injective and that gamma is surjective. And so we're going to do that by chasing through and thinking about this diagram. And so I'm going to need this board space. I'm going to have to erase it. But once we do, then hopefully you can see how that would complete the proof. Okay, what do you want to prove first? Injective or surjective? Injective, okay, great. I want to prove that gamma is injective. What does that mean? Like how can you prove gamma is injective? Very good. So proving it's injective is the same thing as proving that the kernel of gamma is 0, which means that the only thing that maps to 0 should be 0. And so what we should do is let's just pick some element here. I'm going to pick, let's say, orange. I'm going to pick some element here, C, that maps to 0. Right? So let C be some element of C such that gamma of C is 0. So this is my gamma of C. Gamma of C is 0. Our goal is to show C equals 0. Right? Okay. So this is really just a game of following your nose. It's like you just do the only thing you kind of can do at each step and see where it leads you. So like I have this C. What can I do with it? I already know if I take it down, it goes to 0. So instead, I'll take it to the right. That'll take me to some element K of C. Then, if I take it down, I'm at delta of K of C. But by commutativity, delta of K of C is the same thing as K prime of gamma of C, right? So since this is K prime of gamma of C, and we know gamma of C is 0, K prime of gamma of C must still be 0. These are all homomorphisms, so they're going to be saying 0 to 0. So I know that delta of K of C is equal to 0. Okay, so this is equal to 0. But I also know that delta is an isomorphism. So what does that tell you about K of C? It must be 0. in particular, it's injective. So it can only map something to 0 if it's itself was 0. So this k of c is 0. So what does that tell you about c? C is in the kernel of k, because it got mapped to 0. But since this is an exact sequence, the kernel of k is the same thing as the image of j, which means c must secretly be the image of something in j. So pick something here, b, and we now know that c is secretly j of b. So that's what it means to be in the image of j. It's j, it's, something hits c under j. So j of b is equal to c for some b. Okay, so now we've gotten back to b. What can we do with b? It's like the only thing that you can do, like the only thing that comes to mind is you send it down, and now b goes somewhere to some beta of b, right? Okay, let's send beta of b over and see what happens. So j is going to take this to j prime, this is on the bottom, so j prime, of beta of b, right? Okay, but what do you know about j prime of beta of b? By commutativity, this should be the same thing as j of b, which is c, and then gamma. So that should be the same thing as gamma of c. So this is 0, right? Okay, now what can we say? Yeah, this would be in the kernel of j prime. Yeah, that's right. So beta of b is in the kernel of j prime. And if you're in the kernel of j prime, that also means, by exactness, you are in the image of I prime, right? Look, we're really using like this whole diagram. So we're the image of I prime. So what does that tell us? That tells me there's some element here, some a prime, that will map over by I prime, so that I prime of a prime is beta of b, right? Okay. Now we've gotten to the far left. Alpha is an isomorphism. So in particular, it's surjective. So something up here must hit alpha prime. So alpha prime must secretly be alpha of something up here, of some a. So a prime is secretly alpha of a, right? Okay. Now let's think. Let's map a over by I of a. By commutativity, I know that beta of I of a will have to come out to be the same thing as I prime of a prime. But that means that beta of I of a is the same thing of beta of b. So if we just map this down, if we map this guy down, same guy, so it's beta of I of a must secretly be the same thing now as beta of b by commutativity. But beta is injective, because we're assuming this is an isomorphism. So that means that I of a is equal to b. This I of a we just showed is that b. Which means that this j of b must secretly be j of I of a. So what we've shown is, we showed that your c is equal to j of I of a for some a over here. Finish the proof for me. What's the last thing I say now?
Everything in the image of I is in the kernel of j.
Very good. So since this is in the image of I, it's in the kernel of j, in particular when you compose two maps on top, you get 0. Completing the proof. Okay, so we record this so you can go back and rewatch this argument again. I could have written down every step, but I just work on the diagram, right? Okay. We filled up this diagram now, showing that it was injective. So let me draw another diagram, and we'll prove it's surjective. So now I want to prove the gamma is surjective. But to do the diagram chasing, I'm going to need a new diagram because that one's been covered. So let me draw a new diagram. So we have A going to B, going to C, going to D, going to E with some maps between them. I, J, K, L. And then going down, we have A prime, B prime, C prime, D prime, E prime, with maps coming down. I, J, K, L, alpha, beta, gamma, delta, epsilon. Huh? Oh, primes. Yeah, thanks. Okay, and since we're doing surjective now, I'm going to switch to a new color. We're going to use yellow. So how are we going to set up this proof? How do we want to show it's surjective?
Start with something C prime.
Okay, I'm going to start with some little c prime. So I'm going to let c prime, small c prime, be an element of c prime, such that, well, no such that. And then what do we want to show? What do we want to show? Yeah, we want to show something lives up here. We want to show that there exists. I'm not going to call it C because we might use another element called C in the future. So I'm just going to say there's some unknown element X in C such that gamma of X is equal to C prime. Right? Okay. And once again, we're just going to follow our nose. So at each step, we're going to kind of do like the only thing we can. So like, I don't know that gamma is surjective, so I can't just pull them up, right? But what I do know is, well, nothing. And there's a map here, so let's just chase it, see what happens. So I have some k prime of c prime. Okay, what can I do now? Good, delta is an isomorphism. So since delta is an isomorphism, there must be something up here. There must be some d up here that maps down via delta to delta of d, which is the same thing as k prime of c prime, right? Okay. If I were to map this again, what would I get? Well, I would have L prime of either one of these guys would just be 0. So I could say L prime of k prime, of your k prime of your c prime is 0 because it's an exact sequence. So when I do two maps, I get 0. But since these are equal, that's also true that L prime of delta of d is 0. And does this suggest something, this notation? It's like, oh, well, if I start at d and I go down and over, I end up at 0. But that means also if I go over this way and then down, I'll still end up at 0, right? So if I first do L of d and then I map him down to down along epsilon, I would have epsilon of L of d. By commutativity, going over L and down epsilon is the same thing as going down delta and over L prime. So he's the same as him, which we already said is 0. So I know this would map down to 0. But if this maps down to 0, what does that tell me? That means that my L of d must be 0. Because epsilon is adjective. We're using the fact that this is an isomorphism over here. Okay, so that means that d is in the kernel. We're getting the hang of this? D is in the kernel of L. So that kernel of L is secretly the same thing as the image of K. Very good. So that means that there's some C over here that maps over so that K of C is equal to D. Wouldn't it be nice if this is the C we're looking for? Right? Well, these are not the droids you're looking for. We have no way of knowing or suspecting even that this is the right thing. If you think about the C mapping down, you can map the C down. You can map the C down to gamma of C, but there's no reason to believe these equal to each other. We do know that if we map this guy over, via k prime of gamma of that c, if we map him over, k prime of that gamma of c, should be the same thing as this map. So delta of k of c, delta of k of c, which is the same thing as delta of d. So we do know these are equal to each other. So we know that both gamma and c, so both gamma of c and c prime map to the same value. But that doesn't mean they're equal to each other, because we don't know that, we're not assuming, it's not that we don't know, it's not necessarily the case that k prime may not be injective. So like, although we know these both map to the same value, we don't get that they're equal to each other. So now you might think we're kind of stuck. We have two different values that both map to the same value, but they may not be equal to each other, because this is not necessarily injective. So here's the clever move that we do instead. What we're going to do is we're going to think about the difference of these guys. Gamma of c minus c prime. That maps over via k prime to k prime of this difference, gamma of c minus c prime. But we already said that k prime of the first is equal to k prime of the second. So k prime of the difference will just come out to give me 0. Because this is a homomorphism. Right? This is k prime of the first minus k prime of the second, but those are equal to each other. So this difference maps to 0. So this difference is in the kernel of k prime. Now we're cooking again, right? Let this man cook. So if we're in the kernel of k prime, that means we're in the image of j prime. So there's something over here. There's some b prime that maps so that j prime of b prime is equal to this difference, gamma of c minus c prime. Okay, now we have a b prime down here. What can we do with it? Let's bring it upstairs. So there's going to be, since beta is an isomorphism, in particular, since beta is surjective, there's this some b up here such that beta of b is b prime. Okay, let's map this b over. What can you tell me about j of b? Well, I know that when I map over and come down, gamma of j of b is the same thing as j prime of beta of b, and j prime of beta of b is just j prime of b prime. So, oh no, I think this just maps down to this difference. This j of b, this is why I'm doing this in green. This j of b is just going to map down here to gamma of c minus c prime, right? By commutativity. So j of b would map down to gamma of j of b, but that's the same thing as j prime of beta of b, but that's the same thing as j prime of b prime. So that's just j prime of b prime, which is gamma of c minus c prime. Okay, so I have something that maps to gamma of c minus c prime. I have something that maps to gamma of c. How in the world could I get something that maps to c prime? So let me just make this clear. We have that gamma of c is equal to, well, gamma of c. We have gamma of c. And, no, we don't know that it's c prime. We're trying to find something that maps to c prime. And so this one we don't have anything mapping to it yet. We're trying to get to c prime. And we have gamma of j of b comes out to be gamma of c minus c prime.
Gamma of j of b minus
Very good. So hence, gamma of C minus J of B will come out to be, the first guy is just gamma of C, then minus J of B, and that maps to a minus gamma of C plus a C prime, so that maps to C prime. So if we so we know gamma of C minus J of B maps there. So up here, if we take the difference of these guys, C minus J of B, we've just shown that C minus J of B maps that C prime as desired. Okay, good. So we found that it's injective. Surjective and injective. You might want to read through, go through this proof again carefully and keep track of what properties we actually used. Because like in this proof here, to show that this was in to show that that your gamma is injective, we didn't use epsilon at all. And the only thing we used about alpha is that alpha is surjective. And if you look over here, it's like we didn't use alpha at all. And the only thing we used about epsilon is that epsilon is injective. So we didn't actually need that these are all isomorphisms. I've overstated the conditions a little bit. You could weaken it, but it's just easiest to write it as they're all isomorphisms. But you really just need that your alpha is surjective, and you really just need that your epsilon is injective. But I think if you check, we use both, if you combine the two proofs, beta we need as both injective and surjective, and delta as both injective and surjective. We can check, like here we used that it was surjective for beta, whereas over here we used that it was injective, I believe, when we lifted up. So you can go through those proofs and chase through it. You don't actually need that all four are isomorphisms, but that's typically how the proof is used, and so that's how I wrote the statement. Okay, any questions? I highly recommend you've seen it once, but to draw these diagrams and try to do the proof again. Just try and follow your nose. It's a really nice problem to get used to some diagram chasing. But otherwise, we'll stop there, and next week we'll begin looking at some quote-unquote applications of homology theory.